Hello everybody, and welcome to the on-demand webinar presentation of the mobile radio frequency landscape, a patent and technology perspective. My name is Adam Januszkiewicz, and I'm here to introduce our presenter and tell you a little bit about Tech Insights. Today's presentation will cover the mobile RF patent landscape and is an update to a presentation of the same name from 2019, which covered 4G technology. The presentation will be delivered by John Sullivan, a senior circuit analyst at Tech Insights. John has been with Tech Insights for over 20 years and has held multiple roles within the company. John's presentation will begin shortly, but first I'd like to provide a quick introduction to Tech Insights. Tech Insights is the most trusted source for actionable, in-depth intelligence related to semiconductor innovation and surrounding markets. Our content informs decision makers and professionals whose success depend on accurate knowledge of the semiconductor industry, past, present, or future. Our analysis spans a wide range of electronic markets and device types, for which we provide various levels of insight, from product teardowns to material analysis at the atomic level. We offer a suite of subscriptions that are updated frequently with analysis of the latest consumer products. Our unmatched reverse engineering analysis, images, and expert commentary are accessed through the Tech Insights platform, the world's largest research library of semiconductor and market analysis. Our customers include the most successful technology companies, law firms, and licensing entities who rely on Tech Insights analysis to make informed business decisions faster and with greater confidence. Tech Insights is your definitive source for semiconductor analysis. John's presentation will now begin.
Hello, and thank you all for joining me here today. The ultimate value of a patent lies in its evidence of use on products of economic significance. As such, I'm going to touch on three areas in this presentation. First off, market and design wins. This will be an examination of the design wins in the mobile RF space based on the teardown activities that we perform here at Tech Insights. This information can be used as a proxy to assign value to a particular component. The mobile RF patent landscape. This will be a high-level look at the patents of some of the dominant assignees in this space. And finally, I will demonstrate some of the types of analysis that we provide on the Tech Insights platform that can be leveraged for finding evidence of use. The Tech Insights platform contains almost 3 decades of semiconductor data from its teardown activities. Looking at the period between 2018 to present, Tech Insights has torn down and created reports on 600 phones, roughly 140-ish per year on average. 2021 was large with 160 phones, and we have 40 so far in 2022. 60-ish are 5G phones, with 31 being 5G FR2 enabled. This translates to close to 12,000 RF components cataloged, roughly 1,600 of which are unique. These are all components from throughout the RF path of the handset, from the antenna through the front end to the transceiver and modem. These components all came from 83 unique manufacturers. We have 35 OEMs or phone makers and 48 semi companies providing components for the phones. These are a couple of screenshots from the Tech Insights platform. This is where the user can access all the data from the teardown and other analysis activities. This is showing the results of a search on the iPhone 13 Pro Max. Notice the 4 tabs across the top of the page: Summary, Genealogy, Reports, and Images. The screenshot on the left in the foreground has the Genealogy tab selected. This will display all of the components cataloged under this phone. In this case, there are 154 items. Moving from left to right, you see the product boxed in red, followed by the components boxed in blue. You only see 3 here, as the rest are further down the page. The third component is the apps processor, which is a package on package, so there will be another layer of component. The processor and memory component, then you get the die within the components boxed in orange. Clicking on the component or die will bring up the metadata associated with that component or die. Also, clicking on an element within the genealogy will recreate the genealogy with that element at the root. So clicking on the A15 component here, for example, would recreate the genealogy that would show all the phones that this component was found in, essentially showing the design wins. This can be very useful when trying to find components that have economic significance. Assigning value to components is a difficult task, but a good indicator of value are the number of design wins that a component has. The tab on the far right is the Images tab. There are 21 images for this phone, for instance. Since we are at the product level, these photos will be board shots or shots of the subsystems within the phone. If we were at the die or component level, they would be package or die photos or x-rays, for instance. The Reports tab in the center indicates that there are 3 reports created on this phone, one of which is a deep dive teardown report. This slide shows a number of pictures from the deep dive teardown report for the iPhone 13 Pro Max. It's a 220-page PDF. It contains the usual high-level description of the product, as well as teardown images of the phone itself. You get images of all the PCBs and subsystems, as well as x-rays and die photos of the significant components and die within the phone. We also recreate the system level and RF block diagrams. A bill of materials and the costing analysis of the bill of materials is also provided. This slide shows the BOM costing analysis for RF chips within the iPhone 13 Pro Max. Simply a list of all RF chips with their associated piece cost. We see that all ICs cost $328.23. All RF ICs make up approximately 55% of the entire BOM. This translates to $179.40. Now, if we remove the application or baseband processors, we are left with the RF front-end components up to and including the transceiver. These components make up 20%, or $111.95 of the entire BOM of the phone. Turning now to the segment revenues for RF components. These statistics were provided by Strategy Analytics, which was recently acquired by Tech Insights. The small bar chart on the top right corner shows that the RF sector has experienced steady growth from 2019 to 2021, with total revenue increasing from $10.45 billion in 2019 to $11.95 billion in 2020 to $15.52 billion in 2021. This growth will continue, with predicted numbers for 2022 being $16.85 billion. The pie chart on the left shows the breakdown of revenue per RF technology segment for 2019. The segments were partitioned into the following sectors: filters, plexers, low noise amplifiers and PAs, RF switches, antenna tuners, and front-end modules, both primary and diversity. The total revenue was $10.452 billion in 2019. The LNA and PA and filters plexers accounted for more than 80% of this total. The pie chart on the right shows the predicted revenue numbers for 2022 in the same sectors. All sectors will experience steady growth, with the front-end module sector being a large growth area. If we take the 20% number from the BOM cost analysis on the previous slide, we can also estimate the total IC market for mobile at around $84 billion for 2022. The design wins that we are seeing in the front end of the phones we tear down are presented here. This was compiled from an extract from the BOM database on the Tech Insights platform for the years 2018 to present. This will include components from the conventional antenna up to but not including the RF transceiver. Millimeter wave AIPs will also be included here. The pie chart in the top corner probably best summarizes the findings. Murata, by virtue of the filter segment, has the largest part of the pie, followed by Qualcomm. If we look across the tables, we can see that Qualcomm has a large presence in all the sectors of the front end. This is a drastic change from even 4 years ago when their presence was modest. They occupy the top spot in front-end modules, low-noise amplifiers, and millimeter wave AIPs, and second in antenna tuners. Qorvo has the third largest piece of the pie with top spot in RF switches and antenna tuners, and third in front-end modules. Visol is in the mix by virtue of the filter sector. Then we have Skyworks first in the power amplifier sector and second in the front-end module sector. For the most part, we are seeing what we would expect to see. Examining Qualcomm's presence in the front end a little further, the first so-called antenna-to-modem solution was presented in the Sony Xperia XZ2 phone in August of 2018. This phone has significant Qualcomm content in the front end. The block diagram is shown here. The brown boxes are the front-end components, so you can visually grasp the extent to which they are in the front end. Since this time, the number of phones with a predominantly Qualcomm front end has exploded. I have listed some of the models here on the right that we have observed. They're predominantly the low and mid-tier phones. Taking 2021, for instance, of the 160 phones Tech Insights tore down, 81 of them had Qualcomm content in the front end. This is discounting the transceiver and the baseband chips in the back end, purely the front end. And of the 600 phones from 2019 to 2022 torn down, 365 had Qualcomm front-end content. Qualcomm's concerted investment in the front end from 2018 to present has certainly paid off. Turning our attention now to what I'm calling the RF backend. This would include the RF transceiver and applications and baseband processors, or combo AP and baseband. Power trackers are included in the backend as well, as they are tightly coupled with the transceiver vendor. The RF transceiver from the AIPs is also included here. The millimeter wave transceiver architecture is split between the RF to IF section located within the AIP and the IF to baseband on a standalone component closer to the modem. So again, this is an extract from the Tech Insights platform and represents design wins, not unique components. No surprise that Qualcomm dominates in all sectors, except the standalone applications processor, which is topped by Apple, of course. In the standalone baseband category, Qualcomm is also the leader. Second on the list is Intel, but this is as a result of the time frame that this data was pulled from. Intel's numbers dwindle after 2020. The combo AP and baseband, again, is dominated by Qualcomm. MediaTek maintains a presence in predominantly the Chinese market. HiSilicon will continue to drop off. We've seen nothing from them in 2022. Samsung is fourth, with their solution mainly being used within their own phones. For the RF transceivers, it is Qualcomm, MediaTek, and Samsung. Again, HiSilicon and Intel will continue to drop off the list. And finally, Unisoc. We have indeed seen a new Unisoc RF transceiver in a 2022 phone. They are small but present. The FR2 transceiver solution is Qualcomm. We have just recently seen a Samsung silicon in a millimeter wave AIP, and there's news of a MediaTek solution coming out shortly. Power trackers. I'm calling it power trackers instead of envelope trackers, as average power tracking is also being used again for 5G phones. Qualcomm dominates with Samsung, and Qorvo was producing the APT devices. Let's now examine the top 10 smartphone models and the platforms used. These results are for the first quarter of 2022, and again, the statistics are provided by Strategy Analytics. You can see that Apple owns the top 3 spots in market share with their 3 iPhone 13 models. These models both use the A15 plus Qualcomm's SDX60M modem and SDR868 RF transceiver. This configuration is used in both China and the US. There is also an FR2 version in selected markets of the US that use an AIP and transceiver that are both provided by Qualcomm. Fourth on the list is the Samsung Galaxy A12 with the Samsung Exynos 850 and S915 transceiver. There was also a version with MediaTek solution of the MT6765V modem and the MT6177MV transceiver. Xiaomi is fifth with the Redmi Note 10 Pro 5G. Its phones in the German and Chinese markets both use the Qualcomm Snapdragon 865 with its separate STX55M modem and the Qualcomm STR865 RF transceiver. The Galaxy A13 5G is sixth with the Exynos 850 and S915. Seventh is another Xiaomi phone, the Note 11 Pro using the Qualcomm SM8350 and the SDR868. The Galaxy A2 Core is 8th, and it uses the Exynos 7820 and S925D transceiver. Ninth is another Samsung phone, the A32, which uses the MediaTek platform, the MT6853V and the MT6190W transceiver. And then lastly, we have the Honor 55G, which uses the SM7325 and the SDR735 transceiver, both from Qualcomm. It's interesting to note that the Apple phones are the only real flagship phones that made the top 10 for the market share. After the top 3 Apple phones, the list is dominated by Samsung and Xiaomi with their mid and low tier phones. Turning now to the top 10 smartphone models by revenue share, we see a bit of a different picture. This list is dominated by the flagship phones from Apple and Samsung. Again, the iPhone 13 models dominate the top 3 spots. The Samsung S22 Ultra and S22 occupy 3rd and 9th spots respectively. They both have a US model that uses the Snapdragon 8 Gen 1 processor and the SDR735 transceiver. The FR2 version in the US also uses the Qualcomm millimeter wave solution. The European versions of these phones use the Xenos 2200 processor and the Shannon 5520 RF transceiver. The iPhone 12 models and the Galaxy S21 models round out the top 10. It's interesting to note that the first Chinese phone shows up in 13th spot. That was the Honor 55G. This phone was 10th in the model share, if you recall. And then we have the Oppo Reno 7 5G in 14th spot. Mobile RF patent landscape. In this section, I'm going to touch on a patent landscape I created from a number of assignees within the RF space that I identified in the previous section of this presentation. From the previous section of the presentation, I identified the top companies in each of the technology sections within the RF chain. I used 8 of them to create this landscape. Probably no surprises here considering the amount of content that each of these has within the handset. They are the typical RF front-end, transceiver, and modem manufacturers, as well as 2 OEMs in Samsung and Apple. So we have Qualcomm, who has a large presence throughout the entire handset from the antenna to modem. Murata, Broadcom, Skyworks, and Qorvo, who have a large presence within the front-end module and RF switch and filter sectors. There are some notable omissions, and there will be many other entities with RF-related patents. However, for the purposes of this exercise, I limited it to these 8 companies. I pulled the entire active US portfolio for each of these companies and then pruned them down with non-RF technical keywords. These patents were then classified into circuit, process, package, and system. This is a classification that uses TechInsights' years of historical patent data to classify patents into groups based on the reverse engineering needed to support them. These groups can be then examined further to refine them based on technical keywords within the RF space. After the refinement of the circuit, process, package, and system groups, we arrive at a group of roughly 12,000 active US documents. There are granted patents and applications within this group. Plotted here are the patents by priority year. As you can see, there was a steady progress in all 4 groups. The landscape patents are shown here by assignee and the 4 course technical groups. A couple of things stand out. Note the large system candles for Apple, Qualcomm, and Samsung. This is not surprising given they are the modem manufacturers. MediaTek and Broadcom as well to a certain extent. The circuit component is quite large for all assignees as they design chips that populate the components of the front end. Process is not surprisingly low as these are mainly fabless companies. Murata's large spike in process is mainly due to their work in the filter field. Murata is also quite predominant in packaging technologies as well. Further segmentation of the portfolio based on technical areas was then performed. These are still pretty coarse, but segmenting a large portfolio is a process. Starting off on the left, we have the 2 largest groups with roughly 2,000 patents each. These are the antenna and filter sections. The antenna group contains such technologies as millimeter wave patch antenna and package technologies. The antenna candle has been further broken down to show the distribution of assignees within this group. The filter group is dominated by acoustic filter technologies. Our market analysis in the previous section indicated filters as a large growth area. The next candle is the amplifier sector. This sector includes power amplifiers, low noise amplifiers, as well as generic amplifier IP. The RF, TRX, and 5G and mod sections are really catch-alls for topics relating to carrier aggregation, MIMO, modulation, and the like, typically filled with system patents. The comp or components candle relates to the RF components such as inductors and capacitors. Frequency synthesizer category would contain phase lock loop, VCO, phase detectors, and other elements of clock generation. The front-end module section, which was surprisingly small, would contain all the varieties of front-end and power amp modules. And lastly, we have a mixer section and data converter section. The next step in working with the landscape would be to further refine the technical categories with a combination of automation and analyst eyes on. But for the purposes of this presentation, this is the point at which I stopped. A little segment on innovation. This could really be a presentation of its own, but I would like to touch on a few areas of innovation as we are firmly within the 5G phone era and relate them back to the landscape. The drive to reduce complexity, reduce cost, and improve performance has never been more important. The transition to 5G was a gradual one as mobile devices were required to support existing 4G standards as well as the various features of 5G. This has driven the complexity and hence the innovation within the front end. The 4G and 5G FR1 spectrum overlaps somewhat, so an amount of sharing in the front end is possible. For 5G FR2, however, this is not the case. FR2 enabled handsets require dedicated front end resources, which is increasing the complexity of the front end even further. One means of combating this complexity is the increased integration of the front end components into systems in package modules. These modules contain power amplifiers, low noise amplifiers, RF switches, and other frequency-specific components. This is very common. It is not unusual to see the functionality of 29 discrete components, for instance, delivered in a single module. Here is a good example of the integration within the front end. This high-band, mid-band front-end module was found in the iPhone 13. It is a module that measures 7.10 millimeters by 6.64 millimeters and contains 8 die, 3 PA, 1 LNA, 3 RF switch, and 1 RF front-end controller die, and 21 filter dies. This X-ray image shows the die photo of each die superimposed on where they would sit in the module. Note the back side of the package, the small image in the bottom left. You can see that 4 of the die were flip chip bonded to the BGA layer of the printed wiring board of the package. Note the amount of space that the filters occupy as well. These are the pink die in the photo. The number of filters is not surprising given the number of bands that this module needs to support. Complex module integration such as this is what is driving innovation, and if we relate this back to the patent landscape, you could imagine applying circuit process and packaging patents from the amplifier, filter, and front-end module groups of the landscape, among others. Continuing on with innovation, 5G designs continue to expand and optimize existing 4G technologies used to increase coverage and bandwidth of the phone. 5G delivers huge increases in bandwidth. Two of these technologies are MIMO and carrier aggregation. Multiple in, multiple out is quite common in the downlink. However, one of the goals of 5G is to also provide MIMO in the uplink. Carrier aggregation will be expanded with more carrier frequencies being aggregated to increase the bandwidth. Both inter and intra-band CA are commonplace. FR2 enabled phones have their own set of challenges, not least of which are the propagation losses that millimeter waves are susceptible to, thus limiting the coverage of the phone. Beamforming and antenna design is an ongoing area of focus. Power consumption is always going to be an issue, especially with the potential of uplink MIMO. Envelope tracking and in fact average power tracking are also areas of focus. What all this means is a continued innovation at the circuit level and obviously the system level throughout the entire RF path of the phone. Millimeter wave antenna and package technology is an interesting area of focus. There are still a limited number of FR2 enabled handsets. Early millimeter wave AIPs were dominated by Qualcomm, but we were seeing modules from USI and Murata, all of which mostly still contain Qualcomm silicon. But there are now two Murata AIPs that contain Samsung silicon, and we are awaiting the MediaTek AIP in the upcoming Motorola phone to be released shortly. These AIPs incorporate patch antenna elements as well as the RF to IF transceivers and power management chips that perform the average power tracking for the CMOS PAs on the transceiver. The chart on the right shows the distribution of antenna and package related assets from our landscape. Nothing too surprising here, except for Apple. We found that they had some interesting IP in this space. So given the areas of innovation just discussed, we can relate them back to the landscape that we created. Doing a quick search for millimeter wave related patents, for instance, we can see that there are many low-level circuit patents distributed in most areas of the map. For example, drain pump subharmonic mixer for millimeter wave applications, multiband millimeter wave patch antennas, power efficiency and beamforming RF systems, and combining power amplifiers at millimeter wave frequencies, just to name a few. Extensive innovation throughout the entire RF path. Once the target product has been determined and a list of relevant patent assets has been mined, the next step is to find evidence of use. This will require in-depth analysis of the relevant aspects of the target product. Once the analysis is available, the claims analysis can begin in order to ultimately find the evidence of use. Finding evidence of use is enabled by the Tech Insights platform. The Tech Insights platform is the world's largest research library of semiconductor and market analysis. The information contained in the platform can be used to find evidence of use, perform prior art or prior use searches, or can be used for purely competitive analysis reasons. I will now demonstrate some of the types of analysis that are available on the platform that are relevant to the mobile RF space. The mobile RF suite of analysis products begins with an analysis that examines the RF path of the mobile handset. This analysis, which is called the enhanced block diagram, is, as the name suggests, a comprehensive block diagram of the RF path of the handset. The connectivity of the RF paths from the antenna to the RF transceiver, including all passive elements, is determined with continuity checks on the PCBs within the phone. A schematic is then created and delivered in the Tech Insights proprietary circuit vision format. This next analysis involves determining the architecture of an RF front-end module. This analysis recreates the connectivity of all the elements found within the module. The module substrate is delayered and imaged. The dies within the module are decapped and examined, all in order to create a schematic of the module which is as descriptive as possible. This example is a 5G front-end module that serves bands N77 and N78. It is formed with a 6-layer printed wiring board and contains 3 die and multiple passive elements embedded within the package. This detailed understanding of the front-end module also helps to add detail to the elements of the enhanced block diagram that was mentioned on the previous slide. Once the front-end module architecture is determined, we then perform the next level of analysis on selected die within the module. This analysis is a transistor-level circuit extraction of typically the entire selected die. The types of die analyzed will include power amplifiers, as shown in this example, low noise amplifier die, or RF switch and antenna tuner die. Portions of the millimeter wave RF transceiver from antenna and package modules have also been extracted as part of this type of analysis. As with all circuit analysis type reports, this is delivered in a PDF and a circuit vision format. The circuit vision format is essentially the PDF that also contains a schematic and layout viewer. The layout viewer contains the images of the die layers that were used to recreate the schematic of the device and enables cross-probing between the elements of the schematic and the layout. RF architecture analysis. This analysis came about while supporting a high-level patent that revolved around the architecture of the transmit path of an RF transceiver. It was supported with a block diagram like what you might find in a datasheet, but as you can expect, datasheets are pretty rare for these types of devices, so one had to be created. What you are seeing here in the top left corner, the gold image, is the dye photo of the top layer of the RF transceiver. The center image is a SEM image of the transmit section of the die with some of the metal routing information annotated on it. The resulting schematic is in the lower left corner. RF devices are interesting in that characteristic layout features such as high-speed routing, balanced and quadrature analog signal routing, inductors, transformers, and balanced circuit layouts are typically visible within inspection of the top few metal layers of the device. Couple this with the analyst's experience, and a high-level schematic of the RF architecture can be efficiently produced. Depending on the type of patent and the depth of analysis you wish to perform, this block diagram can be quite useful. This type of analysis can also be used to mitigate further in-depth targeted transistor level extractions. Once again, this is delivered in a circuit vision format that allows the cross-probing between the layout and the schematic. This brings me to circuit analysis on an RF transceiver. This type of analysis would be a custom analysis. The example shown here is a full transistor level extraction of an RF transceiver minus the digital areas on the chip. This, as you can imagine, is an expensive and time-consuming endeavor. That is why performing an architecture analysis and zooming in on specific targeted areas for extraction is the most effective in time and money way to proceed. That being said, if you have a large number of circuit RF patents, then a full extraction may be the way to go, as this type of analysis really answers all the questions. I keep mentioning that these types of reports are delivered in a circuit vision format, but for this size of a circuit extraction that involves over 2,000 schematics, the navigational capabilities of circuit vision become crucial and enables the user to quickly develop a deep understanding of the circuitry. I would like to now mention our system's capabilities in the RF space. Although there are no syndicated system type reports in the RF space on the platform, we are capable of performing custom system analysis in the support of specific IP needs. For example, here is a test setup for the system testing of a power amplifier. TechInsights has extensive system testing capabilities in-house and is always on the lookout for syndicatable analysis content for the platform, but can also perform custom analysis where required. The last piece of analysis I want to discuss revolves around acoustic filters. Filters, as I showed earlier, are a high growth area in the RF front end. We have performed custom analysis of acoustic filters in the past. This example, for instance, is on a film bulk acoustic resonator from a duplexer within a phone. The analysis involved planar and cross-sectional imaging to determine critical dimensions and materials, as well as a reconstruction of the filter schematic that included the passive elements within the module in this case. We are in the process of investigating adding this type of analysis to the suite of mobile RF reports in the platform. In conclusion, I touched on three things in this presentation. First off, we looked at the market and design wins from our bill of materials database, which will help in finding products of economic significance. Next, I touched on the mobile RF patent landscape, which explored a little bit of the areas of potential innovation and IP activity. And finally, I demonstrated several types of analysis in the mobile RF space that could prove useful in finding evidence of use. Thank you for your attention.
The analysis discussed in today's presentation showcases content available as part of our intellectual property subscriptions. We offer subscriptions made for patent departments at operating companies, law firms, and licensing entities. These subscriptions help intellectual property professionals find evidence of use and prior art to make informed IP-based business decisions. If you'd like to learn more about TechInsights IP subscriptions, you can email us at info@techinsights.com or visit our website, www.techinsights.com. Thank you, everybody, for joining. This Sorry, I may have been muted there. This concludes the webinar session. We'll now start the Q&A. If you have any questions, please feel free to submit them in the chat window.
Okay, hello everyone. So we have a couple of questions here. The first one is if the materials will be shared. Yes, they will. I'm not exactly sure how, but most likely on the platform. And then secondly, will you have a similar webinar on satellite communication? That's a good idea. Right now, there's no real sector on the platform that covers that, but it's definitely something to keep in mind, and we will definitely consider it. Yes, I see the question about the elaborate more on page 26, the interesting IP. This was really around when we were looking at the millimeter wave antenna and package modules. We did a lot of research just to try and understand what we were seeing in our analysis. And it was, we found a lot of Apple patents in that field. That's simply it. I was surprised to see that many, you know, the antenna structure and how the modules were actually manufactured, because Apple doesn't have an AIP itself. It was curious to see that amount of activity from Apple. Uh, um, how many ARC data types do you have about RX or TX? I'm not sure I understand that question. ARC data type. Yeah, I'm not sure if the question is how many ARC reports do we do per year. It's about on the order of 12 for the architecture, the transceiver architecture. But we like to do all of, we're basically covering all of the available transceivers that come out. That's roughly, you know, 10 or 12 per year. I see a question about typical time taken for a bomb breakdown of a product flagship. Um, I'll try and answer that. I know to do a complete teardown report, it's definitely a couple of months. But the first step is actually to determine the bomb and catalog all the devices. So that is definitely within the first couple of weeks of doing a teardown doing a teardown report. And I do believe the bomb, as soon as it's determined, it's put into the bomb database on the platform. So we're not waiting for the teardown report to be complete. Do you also perform such analysis for other wireless consumer electronic products, access points, smart speakers, streaming players? To a certain extent, we do look at Internet of Things transceivers. So it would be speakers, wearables, and things like that. Access points, occasionally we have, but we like to target the more for the mobile RF anyway. It's mainly around the cellular RF devices from the smartphones, basically. But it's the same kind of analysis, so it's a matter of, we can do it. It's just on a different product.
Okay, everyone, if there's no other questions, this will conclude the Q&A session for this webinar. So just as a reminder that the slide deck and on-demand video link will be shared in the coming days with a follow-up email. And the analysis discussed in today's presentation does showcase content available as part of our intellectual property subscriptions. To learn more about Tech Insights IP subscriptions, you can email us at info@techinsights.com or visit our website at www.techinsights.com. So thank you so much for everybody for joining us. Thanks, John, for presenting, and have a great day.
Thank you.